Swayam Prabha. Digital India. Educated India.
I welcome you once again for this flow through porous media. We are discussing about this introduction chapter. So, we are in the topic introduction, where we are discussing about the most basic features of porous medium and how they are going to help us in different applications. We are discussing about definition of porous medium, what are those major characteristic parameters of a porous medium, and what are the major applications. So, in my last lecture, I was discussing about these restraint to flow and superficial and interstitial velocities, and we discussed about this Darcy's law. What we said, the Darcy's law says that V superficial is equal to K by mu. We just now said it is P A minus P B. In our last lecture we showed that K by mu P A minus P B divided by L. So, this superficial velocity, it has P A minus P B. P A minus P B is basically the pressure at position A minus pressure at position B divided by L. So, we have a pressure gradient. So, we said that this relationship is more like a cause and effect relationship. So, we have this is the effect, and effect is proportional to the cause. What is the cause? Cause is the pressure gradient here. So, we have cause is basically the pressure gradient. I have a pressure difference P A minus P B and over a length L. So, the gradient is equal to P A minus P B divided by L, and what is the effect? I have a velocity, I have a fluid flow taking place. So, the velocity is the effect. So, and this the constant that we have here is basically K by mu. Mu is the viscosity, it depends on what type of fluid we are running through this porous medium. If it is water, it is close to 1 centipoise. If it is honey, the viscosity would be much higher, and K is the permeability. Now, one can write these instead of in algebraic form, one can write this in differential form, and that differential form would be V superficial is equal to minus K by mu del P del x. So, this is the velocity in differential form. So, it is minus K by mu del P del x. Why minus sign? Because I expect that when there is a flow taking place, if there is a flow taking place, and if I plot pressure versus distance x, I would definitely see that the pressure will decrease. Flow will take place from high pressure to low pressure. So, pressure will decrease as you go from inlet to outlet. So, what that means is the slope of this line, which is given by del P del x, itself is negative, but you have, if x is the velocity in the x direction is positive. So, one needs to have this minus sign. In fact, if you convert this to algebraic form, if you assume the pressure profile to be linear, in that case this del P del x would be, you will write it as P B minus P A. So, this minus sign will make it P A minus P B, which is the algebraic form that I mentioned here. So, this form of equation we are going to use more often, that V superficial is equal to minus K by mu del P del x. Now, this here obviously if we want to bring in the V interstitial would be then you have to simply divide one, we have to have one extra term phi in the denominator. So, this would be, this is going to be the interstitial velocity. So, this is one good thing, because when we work with this kind of so we are seeing a sort of a structure here, how we can relate this flow through porous medium just like the way we do just with what we did in fluid mechanics, because in case of fluid mechanics also we have a velocity against a pressure gradient when there is a flow of fluid through a pipe. So, we can somehow we can start thinking in those lines. Okay. Of course, there we do not have permeability as such, that is something which we need to dig into a bit, but essentially this pressure gradient and this cause and effect type relationship is gelling with what we had already learned, what we had already studied in fluid mechanics in the context of fluid flow through a conduit, through a pipe. So, that is one good thing, and we have this porosity and how the porosity relates superficial velocity with the interstitial velocity, or in other words, I have this Darcy's law which is taking care of the overall, in an overall sense, what is the velocity, which we get directly from Q directly by dividing directly from Q divided by A, we call this superficial velocity, and how we can relate these to the local velocity, interstitial, inside the pores. So, how they relate we can see from these equations, and all these two equations, these equations are, you mind it, these equations are valid only when your only when, see, we have to pick up a dx, right, whenever we write this kind of an equation, we essentially our x starts from here. So, x starts from here. So, this is x. So, we pick up a differential length and we call this differential length as dx, right. So, this differential length that we have here, which is basically dx, this dx differential length has to be large enough so that we do not get into the trap of that sampling volume below that threshold volume for definition of porosity. So, that we must keep in mind, that we are assuming that this material is homogeneous, or even if it is heterogeneous, we have the length scale is different. We are not going to that sampling volume which is less than the threshold value, for which we need to consider discrete changes in velocity. Here you can see V superficial velocity, that means here we are considering uniform velocity in this direction. So, we are assuming, see, there is no function of z. So, we are assuming all these, they are having the same velocity, and that velocity is given by this. But if you have a porous medium with these grains, so how the flow takes place? It is taking a turn here, then turn there, and going round and round and doing all those things, right. So, what we are assuming is that as if I have a continuum existing, my flow is being restrained, but that restraint is all taken care by this permeability term K. So, that will take care of how much would be the pressure drop, etc., but I will assume that a continuum exists and the velocity is uniform, the actual velocity is like this. So, this is a major assumption, that you are considering this porous medium to be homogeneous, your reference volume, your reference sampling volume is large enough to draw this kind of continuity. Now, this is the trend, this is what we are going to do in case of porous flow through porous medium. Depending on, I mean, there are some ways to get into this discrete modeling, though one needs to get basically this type of continuum approach is worked excellently well, worked very well for various applications that we are going to design. So, that is why we have I can tell you that, I mean, have full confidence on this continuum assumption in this case, because this has been used in almost all applications, and people have done their design very efficiently with these continuum assumption. So, what we have next is so called pore size distribution. This is also another important thing we must keep in mind. We have been talking about permeability and porosity and all this, but these pores, they are not of uniform size. So, if we try to plot fraction of total number of pores, let us say I or number of pores or fraction of total number of pores, either way, versus the let us say I write pore diameter. And here I write fraction of total number of pores. So, what we expect here is some pores will be large, some pores will be small, some are not so large. So, there would be various sizes of pores present in the porous medium, because it is a random structure. Had it been a monolith of uniform, we have approximated porous medium as a bundle of capillaries. There we can think of all capillaries of same diameters, they are running through the rock, they are running through that solid. So, that kind of porous medium, they will have a fixed structure. The pore diameter is all a single pore diameter is not varying, it is just a single value, single diameter. But in a real porous medium, in a random porous medium, you will have all diameters present. So, in this context, you can have something like you have some pores of diameter, let us say 1 micrometer. 1 micrometer means it is equal to 10 to the power minus 3 millimeter, or you can write 1 micrometer as equal to 10 to the power minus 6 meter. So, one can have pores of these dimensions, one can have pores in the nanometer range, one can have pores even less. So, in this case, you can define the porous medium depending on what kind of what type of pores are dominating in this. For example, if we look at a sandpack or a sandstone which we get from Mother Earth, sandstone where most of the oil is held up, many a times you get water. So, these sandstone, these are so called porous rock. There the diameter, pore diameter or pore width, pore opening is to the tune of 1 micrometer or even larger. Whereas, there are porous medium which are having much smaller pores. For example, this carbon material, they are highly porous. What I understand is that a very small piece of carbon can hold a football field worth of surface area tucked inside. So, they are highly porous. So, this carbon porosity, the pore size is at a much smaller range. Carbon has mostly so called micropores. In this context, I must point out that you can have, if you are in this range, let us say I have 2 nanometer to, let us say, about 50 nanometer. This range is referred as mesopores. Okay. 2 nanometer to 50 nanometer, and higher generally we call it macropores, and below 2 nanometer we refer them as micropore. Okay. So, you will find that the porous medium that is provided to you, that has substantial amount of this, then some this like this. So, a porous medium could be, so you will find fraction of total number of pores, there may be good number of micropores present, there are some mesopores present, some are macropores are also present in this. So, you will have a pore size distribution like this. Generally, generally the whenever you have a micropore and mesopore, this kind of combination one can get in carbon. In fact, carbon which has some amount of mesopore, let us say 80% or 90% of pores are micropores, 10 to 20% are mesopores, that kind of combination is very useful. One can access that area, and this can be used, I'll discuss this can be used in many different applications. Whereas in case of macropores and even larger, 1 micrometer and even larger, they are used for applications such as oil recovery from underground reservoir, water from underground reservoir one collects water also, or maybe sequestration of various chemicals inside mother earth. So, in these are basically the macroporous regime. Of course, there are engineered products which uses all these pore sizes, but essentially this kind of a distribution one can have, these micro, meso and macropores and their combinations. Now, when it comes to flow through macropore, when we are talking about these Darcy's law and this V superficial as minus K by mu del P del X and all these are primarily meant for this part. So, this part we are more there you will find these to be applicable more. Whereas, as you are going down, as the pore size decreases, you will find that there would be some other mechanisms governing the transport process. What are those? For example, what did we consider when we talked about Darcy's law? We talked about basically the Poiseuille's flow. I mean, if you refer fluid flow, if you refer the fluid mechanics in this context, it would be Poiseuille's flow. Simple flow through a pipe, flow through a channel, that will have a pressure gradient and you will have some resistance, and so these are some things which we had done earlier. Probably we are more familiar with something called friction factor in case of flow through a pipe. Here we see permeability. So, this part is the flow through macropores. There you will have this kind of Poiseuille's flow, or you can call it in very simple term, you can call it viscous flow. I think the viscous flow, because you have a viscosity term K divided by mu after all. So, this viscous flow is governing when we are working in this region, when the pores are primarily macropores. But as you go down, when the pore diameters are small, you will find there would be other mechanisms that are coming into play. In fact, down the line we will discuss this in detail. Transport can be thought of as few other types of a flow that takes place through a porous medium, they can have this kind of parallel circuits. So, let us say the bottom one we can write this is for the viscous flow. Okay. So, here you have macropores and viscous flow is taking place. Here the top one I can write this as bulk diffusion. What is bulk diffusion? Bulk diffusion is that if you put some ink in a beaker full of water, you will find that the ink percolates, ink quickly travels and fills the beaker completely. So, you put a drop of ink in a beaker full of water and the ink travels. It is because the process is known as diffusion. it has its own Brownian motion and it travels into this. You are not imposing any pressure gradient to the ink for travel. So, you can have this kind of bulk diffusion for the so you can have some molecules can travel through pores by the method of bulk diffusion. There is another process which goes by the name Knudsen diffusion. Knudsen diffusion. Knudsen diffusion, I believe you have studied in the in physical chemistry. Knudsen diffusion is that there is molecules are traveling through the pore, but molecules are colliding with the wall. Generally, when the pore diameter, when this pore diameter, let us say pore diameter is d, and the mean free path, that length is lambda. So, it depends on what is the value of lambda by d. What is the value of this lambda by d? When this lambda by d they are close, then you will see that the collision of molecules with the wall that governs the flow, that influences the flow. So, one has so this is basically this. See, as you decrease d from the macropore range to on the lower side, you will at one point of time the mean free path length of these molecules that are traveling and the diameter of the pore, they would be close to each other. In fact, there is a dimensionless number in this context which goes by the name Knudsen number. So, when this number is close to 1 or so depending on some threshold number, you will find that this kind of transport mechanism they start dominating. Similarly, here you will find that there would be a process known as surface diffusion. Surface diffusion means that molecule that is supposed to travel, molecule will get adsorbed to the inner wall of the pore, and then the diffusion is taking place through the surface. That means it is not a bulk diffusion. That means it is not molecules colliding with each other in the bulk and traveling through the center of the pore. Molecule first gets attached to the inner wall of the pore, and then by means of surface diffusion it is traveling. So, there are various mechanisms that are various transport modes by which molecules can travel through porous medium. And when we talk about Darcy's law, when we talk about superficial velocity that we discussed in the last lecture, that is because of viscous flow. Okay. It could very well be that that the pore size that one works with, you are at this viscous flow and Knudsen diffusion. These two parallel lines are working. Surface, you are not bothered with the surface diffusion. In fact, we will show that when somebody works with flow of gas through shell is some subsurface material in which lot of hydrocarbons are stored, and nowadays people are extracting hydrocarbon out of those shell layers. So, you will find that this diameter is very small, and it is the lambda which is the gas, the mean free path. So, when you are talking about flow of a gas through a shell layer, one may have to consider viscous flow, that is fine, and on top of that maybe Knudsen diffusion. So, there could be combination of these transport mechanisms also possible, combination of these transport modes. So, I mean, though we discussed this viscous flow, though we talked about Darcy's law and the cause and effect and pressure gradient, just be aware that there are other transport modes available, and there could be combination of transport modes. Of course, it depends on what pore size distribution you have here, you are working. So, with this understanding, now let us see what we have next. We talked about this permeability. Permeability was in case of Darcy's law, right? In case of Darcy's law, we had this definition of permeability. What was the Darcy's law? We had written there as V superficial is equal to minus K by mu del P del X. So, this K is what we said is the permeability. So, a medium, the definition of permeability is something like this: a medium with a permeability of 1 Darcy. Mind it, Darcy is one unit of permeability, just like meter is a unit of length. So, permeability of 1 Darcy permits a flow of 1 centimeter cube per second of a fluid with viscosity 1 centipoise. 1 poise means gram per centimeter second. So, 1 centipoise would it be 10 to the power minus 2 gram per centimeter second, which comes to 1 millipascal second. So, a viscosity similar to water when it flows through a porous medium under a pressure gradient of 1 atmosphere per centimeter. So, pressure gradient is 1 atmosphere per centimeter. That means, if this is the length of the core, and if this is 1 centimeter, the pressure drop over this length 1 centimeter is 1 atmosphere. So, pressure gradient of 1 atmosphere per centimeter acting across an area of 1 centimeter square. So, the area here is 1 centimeter square and the pressure drop is 1 atmosphere. So, under such condition, if one gets a flow rate of 1 centimeter cube per second, then one call this porous medium is having a permeability of 1 Darcy. So, that is the definition of 1 Darcy. Now, typical values for gravels are, you know what gravels are, gravel pack we have seen. For gravels, it could run up to 100,000 Darcys. That is too high. I mean, I would say if you work with a sand pack, it would be of the order of Darcy, to less than 0.01 micro Darcy for granite. So, Darcy is a unit of permeability, and approximate permeability of sand is 1 Darcy. So, 1 Darcy is equivalent to some meter square you have written here. It is close to 10 to the power minus 12 meter square. So, 1 Darcy is equivalent to approximately 10 to the power minus 12 meter square. So, you must note that in SI unit, this unit of permeability is meter square, which would be obvious. V superficial would be meter per second. You put this del P del X, del P would be Pascal and X, the length would be meter. So, Pascal per meter, and this viscosity you put it as kg per meter into second. So, put viscosity as kg per meter into second, pressure drop as Pascal, length as meter and superficial velocity as meter per second, you will find that unit of permeability will come as meter square. So, Darcy and meter square, this is the relation. 1 Darcy is equivalent to 10 to the power minus 12 meter square. So, this is how the best, this is what is the basic definition of 1 Darcy. So, with this understanding, I mean, we have more or less got some glimpses of how this flow through porous media is going to, and what all we need to touch upon at least in this course. Next, what I am going to discuss is the applications, but that would be the next lecture. So, with this understanding, I am closing this lecture here, and I will continue this lecture with the application section of introduction to flow through porous media. Thank you.